The 8086 microprocessor, it can operate in two different modes. One is the maximum mode and the other is the minimum mode. The difference between the two modes is that in the minimum mode, there is only a single processor in the system, and whereas in the maximum mode, there are more than one microprocessors in the system. In the minimum mode, the 8086 microprocessor, it derives the status signals and it controls, it is going to provide all the control signals to the systems present in the to the devices which are present in the system. Okay, so in the minimum mode, there is only a single processor, that is the 8086 microprocessor, and that will be the master because it is providing the control signals to the various other devices in the system. Whereas in the maximum mode, because there are more than one microprocessors, so the 8086 microprocessor, it is going to give the status signals. That status signals will be given to a bus controller. That bus controller is going to provide the control signals. So the control signals, they are not directly provided by the 8086 microprocessor in the maximum mode. So if we talk about the differences, in minimum mode, there is only a single microprocessor, but in maximum mode, there is more than one microprocessor. In the minimum mode, the 8086 provides the control signals, whereas in the maximum mode, the bus controller provides the control signals. Now, how these modes are selected? In the 8086 microprocessor, we have a pin which is decided for the minimum and the maximum mode selection, which is known as MN/MX bar. This pin is allotted in the IC of the 8086 microprocessor. When this pin is at logic 0, then maximum mode is selected, and when this pin is at logic 1, then minimum mode is selected. So the next difference we have is when the minimum and the maximum pin, it is at logic 1, then minimum mode is selected, and when the minimum and maximum pin, it is at logic 0, then maximum mode will be selected. So these are the two modes of operations of the 8086 microprocessor. Let us study these modes in detail. First, we will start with the minimum mode of 8086 system. So in the minimum mode, there will be only a single microprocessor, and that will be the 8086, and all the control signals, they will be provided by the 8086. This mode is selected when the pin MN, MX pin is at logic 1. There is a single microprocessor So these features we have already studied about the minimum mode of 8086, that when this pin is at logic 1, then minimum mode is selected. There is only a single microprocessor in this mode, and all the control signals, they are given out by the microprocessor chip itself. Now if we see the diagram for this minimum mode, then this is the diagram for it. It is the minimum mode 8086 system. In this block diagram, you can see that here we have the 8086 microprocessor, which is providing all the control signals like memory input output, read, write, bus high enable, address latch enable, then address and the data bus, data transmission and receive, data enable, and here the reset, clock and ready signals, they are given to the 8086 microprocessor by this clock generator IC 8284. This is the clock generator. Here we have the 8086 microprocessor. Here we have a demultiplexer. Okay, so this demultiplexer, it is using the memory input output, read and write signals, and it is providing 4 types of signals which are for memory read, memory write, input output read and input output write. So these signals, they are combined together and their combination signals are generated. Then we have here the chip select logic. Here we have the memory, the RAM, ROM and input output devices. So if we want to select, suppose RAM is to be selected, then its chip select signal will be provided by this chip select logic. Then if ROM is to be selected, then that will be also provided by this chip select logic, and it is having the input as bus high enable and the A0 address line. Then it is providing the chip select for input output also for RAM and ROM. Okay. Then we have the 74LS373 latch, which is a type of D flip-flop. So here we have the latches. Okay. Then we have a trans receiver here. So this trans receiver is used to either transmit or receive the data, and that is 74245. Okay, so in this minimum mode system, you can see that there is only a single processor, and this processor is providing all the control signals to the other devices which are connected in the system. So if we talk about the elements which are present in the minimum mode, we have latches, we have a trans receiver, clock generator, memory and input output devices. A chip select logic is also there. So this was about all the elements which are present in the block diagram of this minimum mode. Okay. Now let's come to the working, that how these elements, what is the function of each of the block in this diagram. We were having latches here. So latches are generally the buffered output D flip-flops. Whose IC number is 74LS373 or 8282. These latches are used for separating the address and the data, because in the 8086 microprocessor the address and the data bus they are multiplexed with each other. Address bus is of 20 bits and data bus it is of 16 bits. So 16 bits of data bus they are multiplexed with the 16 bits of address bus. So if we want to separate this address and the data bus, then latches are used. So here you can see the latch is there, the input is the address and the data bus which is multiplexed, and this is separating the address and the data from each other. So these are used for separating the valid address for separating the valid address from the multiplex address and data signals. Now these latches they are controlled by the ALE signal. ALE signal is the address latch enable. So this signal it enables the latch, it is used to enable or disable the latch. So when this signal is high, then only the latch is enabled, and when this signal is low, then the latch is disabled. So to enable or disable the latches, then we use the ALE signal. So we can say that this signal controls the latches. Okay. Next element we have in the block diagram are the transceivers. Transceivers, it is the combination of the word transmitter plus receiver. Okay, so we can say that it is transmitting the data also and receiving the data also. So because they are acting in both the directions, so they are the bidirectional buffers. So latches are used to separate the address from the address data bus, and transceivers they are used to separate the data from the address and data bus. Okay, because that data will be transmitted or received by the microprocessor. So data has to be separated, and that is done by the transceivers. Now these transceivers they are controlled by two signals, DEN and DTNR. Okay. This DEN is for data enable. These are used to enable or disable the data buffers, and this is for data transmission and receive. So when this signal it is low, 0, then data will be received, and if it is 1, then data is transmit. So these two signals they control the transceivers. You can see here that in the transceivers we have the two signals from the 8086 microprocessor which are connected to the enable line and also the direction control line of this transceivers 74245. Okay. Now next we have the memory part. In memory we have both type of memory, RAM and ROM. Now RAM is used for storing the user's program, and ROM is used for the monitor storage. Okay. Here we have a input output system also. Okay. So these are the various blocks here. Clock generator, it is providing the clock pulse to the 8086 microprocessor. Demultiplexer, it is providing the control signals, generating the control signals by having the signals from the microprocessor, combining them, producing the memory and the input output read and write signals. Latches are used to separate the address from the address and the data bus. Transceivers, they are used to separate the data from the address and the data bus. Then memory is used to store the program, user program or the monitor program. And input output devices, they are also used to interface with the 8086 microprocessor. So these are the different elements which are present in the minimum mode 8086 system. Now let us come to the working of this minimum mode system, how the microprocessor works in it, what are the various clock cycles involved in it. Let us see. So the working of the 8086 in the minimum mode, it can be easily explained with the help of the timing diagrams of the clock cycles. We have different clock cycles like the opcode fetch, memory read, memory write, and input output read or input output write. So here we are going to study the timing diagrams of the different clock cycles. So the timing diagram for the minimum mode of the 8086 microprocessor, we have the three machine cycles are there: opcode fetch, memory read and memory write. The timing diagram for the opcode fetch and the memory read cycles, they are similar, and so the timing diagram, we can say that it consists of two cycles. One is the memory read and second part is the memory write. First, we will study about the memory read machine cycle. So as the machine cycle, it is in response to the clock cycle. So we have here the clock pulse. Then this memory read machine cycle, it is started by the address latch enable signal, that is ALE. So the machine cycle, it consists of various T states. So during the first T state, that is T1, the read cycle will begin with the assertion of the signal ALE, means when this signal is high, then this signal will be high in the T1 T state, and also the memory and the input output signal, that will decide that whether this will be a memory read machine cycle or an input output read machine cycle. So whether it's a memory option or it's an input output operation, that will be decided by this signal. So both these signals, they will be made high or low in the T1 T states. Then we have the bus high enable and A0 address signal. So these two signals, that is bus high enable and the A0 signal, they can have low, high or both bytes. Means they can take any of the values. And this memory and input output signal, that from T1 to T4 T states, this signal will decide that whether it's a memory or an input output operation. So if we'll draw the timing diagram for the memory read machine cycle, then this will be our clock. that is ALE signal. So when the signal is high, then address will be placed on the address bus. We know that 8086 microprocessor, it is having 20-bit address line from A0 to A19. So from A0 to A15 it is multiplexed with the data bus, and A16 to A19 they are multiplexed with the status signals. So here we have the this is the address and the status signals. Bus high enable signal. So when this signal is high, then address is placed on this address and status bar, and after the T state, then we will have the status signals over here. Next we have the address and the data bus. So when this address latch enable signal is high, then address is placed on this address and data bus, and when this signal goes low, then valid data is available here. Okay, so when this reach signal is low, that means when the signal is activated, then this valid data will be read by the microprocessor, and that data will be available on the address and the data bus. Okay, so at this T2 machine cycle, the address is removed and then data is placed on this address and data bus, and then that data will be read by the microprocessor. So if we describe this machine cycle, then at T2, the address is after that, when the data has been removed and it has been sent to the input, then the bus is then tri-stated. So you can see here that when this read signal is low, then valid data is available on the data bus, and then that data will be read. Okay, so here we have the you can see that after this T4 T state, this signal is high, so these buses they go to the tri-state condition. Okay, now let's come to the memory write machine cycle. Just like the memory read machine cycle, the memory write machine cycle, it also starts with the address latch enable ALE signal, and then bus high enable and the memory input output read that signal will decide that whether it will be a memory operation or an input output operation. Let's see the timing diagram for it. This is the write cycle timing diagram for the minimum mode. Here we have the clock cycle. We have T1, T2, T3, then TW is the wait state, and then we have the T4 state. Okay, then this is our address latch enable signal. Then this is bus high enable signal A19 to A16, the address bus, and then we have the status signals. Then address and data bus A15 to A0. When this signal is high, ALE signal, then address is available. When it is low, then data is available on this bus. Then this right side signal, it goes low from T2 to T4. So during this, when this write signal is low, then this valid data will be written to the buses to the output. Okay, then we have the data enable signal and the data transmit and receive. So this data transmit and receive signal, this is high. It means data is going to be transmit. Data will be transmit to the output device. Okay, so that data which is available on the address and the data bus, that data will be written to the output device. So if we describe here the write cycle, so it is going to start with the assertion of the ALE and the emission of the address. So when the address is placed on the address and the data bus, and when this ALE signal is high in the T1 T state, then memory write machine cycle will start. That is the write cycle will start. Now, this can be the memory write machine cycle also, and the input output write machine cycle also. Write operation is the same, only the memory and the input output devices, they have to be decided. So that will be decided by the memory and the input output signal. Okay, so when this signal is for memory, means when this signal is low, that means it's a memory operation, and when the signal is high, it means that it's an input output write cycle. So it is going to decide that whether it's a memory or input output operation. So in this T2 T state, after sending the address in T1 T state, the processor sends the data to be written to the address location. So you can see here that in the T1 T state, we have the address here. So when this T2 T state starts, address is already sent to the microprocessor, and then in T2 address is available, and that address will be data is available, and that data will be written to the location, memory location, whose address is given in the T1 T state. So address is already with the microprocessor. So at that memory location, that this valid data will be written by the microprocessor. So the data that is available on the bus, it will be available till the middle of the T4 T state. You can see here we have the data here. This is the T4 T state, and till the middle of the T4 T state, that data will be available on the bus. Then we have that this write signal, it becomes active at the beginning of T2 T state. You can see here that this is the T2 T state. Until T4 this write signal is active. This is active means this value is low. So when this signal is active, that data will be written to the memory location. Then we have the bus high enable and the A0 signals. These signals are used to select the proper byte or bytes of data. These signals will decide that whether and 8-bit data or means 1 byte or more than 1 byte of data has to be transferred. So that is decided by bus high enable and the A0 signals. So these signals are available here. A0 address line is here, and bus high enable signal is also available. Then data transmit and receive signal, because this signal is high means data is going to be transmit. Then we have the data enable signal. So when the signal is low, then the transceivers, they are activated. The transceivers, because they can transmit and receive the data also, so at this time they are going to transmit the data. Okay. Then we have the signals: memory, input output, read and write signals. Memory, input output, read and write signals. So these signals, they are deciding that whether this is a memory read, memory write, input output read or input output write machine cycle. The timing diagrams are same. Timing diagram for read and the output fetch machine cycle, it is same. And then we have the timing diagram for the write machine cycle. So these are the timing diagrams of the different machine cycles when the microprocessor, it is working in the minimum mode. Minimum mode means that all the control signals like this memory, input output, read, write, ALE, bus high enable, all the control signals, they are provided by the 8086 microprocessor only. Okay. Next, this 8086 in the minimum mode, it is also going to provide the bus grant and request signals. Suppose that some input output device and peripheral devices like input output and memory, these are connected in with the 8086 microprocessor. Now when these input output devices, they want the control of the buses of 8086 microprocessor, or like DMA is connected in the system, so that DMA, direct memory access controller, if it wants the control of the buses of 8086, then the 8086, it is going to give the grant and request signals to the other controllers. So here next we have the bus request. We have two types of signals: bus request and bus grant signals. So let's see the timing diagram for these signals. The bus control is asked by the peripheral devices like DMA. We have the DMA controller, direct memory access. So this controller, it is going to send the signal hold to the microprocessor, and in response to this hold signal, microprocessor is going to send the hold acknowledge, that is HLDA signal. So when this hold signal, it is checked by the microprocessor at every leading edge of the clock pulse. So whenever at the leading edge of the clock pulse, if this hold signal is received by the microprocessor, then microprocessor at the next clock pulse, it is going to give the signal HLDA. Hold means that this DMA controller, it wants the control of the system buses of the 8086 microprocessor. So when this hold signal is received by the microprocessor at the leading edge of the each clock pulse, it is checking, and if it is received, then HLDA will be granted by the microprocessor. So the control of buses will be relieved to the direct memory access DMA controller. So we have the two signals here, hold and HLDA. So this hold is checked at the leading edge of each clock and if it is received by the microprocessor during the T1 T state or the T4 T state of the current instruction which is executed by the microprocessor. So at that time, if it is received, this request is received, then CPU is going to activate the HLDA hold acknowledge signal in the next clock cycle. Okay, and when this signal is given HLDA signal, then the bus control is released to the other microprocessor or the other requesting master which is requesting the control of buses. Now the control of the buses when it is given to the other master, so that will not be regained by the microprocessor until and unless the requesting master does not drop the hold pin low. So if this hold pin is high, then the buses will be under the control of the other master, other controller. When this hold signal is dropped by that requesting master, then only the control of buses will be regained by the microprocessor. And when the microprocessor regain the control, then the hold acknowledge signal will be made low in the next clock cycle. The trailing edge of the next clock, the HLDA will be dropped by the processor. So first hold is given to the processor, then if hold is received by the CPU, then it is going to give the hold acknowledge signal. Hold acknowledge signal will be given to the requesting master. Then that master is going to drop the hold signal. When hold signal is dropped, means it's made active low. Then HLDA will be made low at the by the microprocessor at the trailing edge. If this is the clock pulse, then this is the leading edge and it is the trailing edge. So at the trailing edge of the next clock pulse, this HLDA signal will be dropped by the microprocessor. So these are the bus request signals and bus grant signals which are issued by the microprocessor during the minimum mode. Now let's come to the minimum mode interface. Minimum mode interface means that all the devices which are connected to the 8086 microprocessor during the minimum mode configuration. So during the minimum mode interface, we have seen the block diagram that in the minimum mode, we have the 8086 microprocessor and then different signals are there which are given by this 8086. So these signals, they can be characterized as we have the address and the data bus here. We have the status signals also. We have the control signals, interrupt signals and the DMA signals. DMA signals include the hold and the hold acknowledge signals. Interrupt signals means that INTR and INTA signals, and address signals are the address and the data bus, and status signals are S0, S1, S2 till S7. So let us see that what are these signals, what are the functions of these signals. So that will become under the minimum mode interface. Interface means that the path which is providing the communication path between two components. So in the minimum mode system, we have the 8086 microprocessor and other devices like the clock generator, we have the latches, we have transceivers. So how the microprocessor is communicating with all these components. So the signals which are used that are described under this topic. So in this we have the address and the data bus. So these are the different signals which are needed by the microprocessor in the minimum mode. First, we will start with the address and the data bus. In 8086 microprocessor, we have the 20-bit address bus starting from A0 to A19. Data bus is of 16-bit. D0 to D15. Now this address and the data bus, they are multiplexed with each other. So we have AD0 to AD15. And rest of the address lines, that is A16 to A19, they are multiplexed with the status signals. The word multiplexed means that during the machine cycle, so during T1 T state, this bus is going to act as an address bus, and during the T2 machine cycle, it is going to act as a data bus. Okay, so same bus is acting as the address bus and the data bus. So these are the address and the data bus of the 8086 microprocessor. Then we have the status signals. So as I have said that the A16 to A19 address bus, it is multiplexed with the status signals. So the status signals, as I have said that the A16 to A19 address bus, it is multiplexed with the status signals S3 to S6. So A0 to A15, it is having the data also on it, that is D0 to D15. And A19 to A16, it is having the status signals S6 to S3. So at the time when this address is available, that is A0 to A15, at that time A19 to A16 is also having the address over it. When this address bus is having data over it, at that time this bus is having the status signals over it. Okay, so at this time we have A19 to A16 address. So complete address will be available on the address buses, and when this bus is acting as a data bus, then at that time this will be having the status signals X6 to S3. Now let us see that what is the function of these status signals. The signals S4 and S3, these signals are uh, used to select the segment registers which are available in the 8086. In 8086, we have the 4 segment register: code segment, data segment, stack segment, and extra data segment registers. So to select the segment register, so that the segment address of the memory location, it can be identified, these status signals are used. So these two signals, they have different combinations. Let's see S4 and S3. If it is 0 0, it can be 0 1, 1 0, and 1 1. So we will have different segment registers selected. If it is 0 0, then extra segment register is selected. If it is 0 1, then stack segment. If it is 1 0, then code, and when it is 1 1, then data segment registers. So this S4 and S3 status signals, they are used to identify the segment register, and when the segment register is known, then we can identify the segment address also, and that segment address will be used to form the physical address of the memory location. Next we have the status signal S5. Now this status signal is also used to identify some internal characteristic of 8086 microprocessor. Its logic level, it is the logic level of the internal enable flag. So to enable or disable this internal flag, this status signal S5 is used. Then we have S6. This S6 is always kept at logic 0. Okay. So we have the status signal S3, S4, S5 and S6. S3, S4 they are used to identify the segment register. S5 is used to enable the internal flag, and S6 it is always kept at logic 0. So these are the status signals used by the 8086 microprocessor. Next we have the control signals. Now control signals, they are used to decide the interfacing, the memory or the input output interfacing of the 8086. The control signals, we have address ALE, we have the bus high enable signal, then we have memory and input output signal. Also we have the data transmit and receive signal, and we have the data enable signal also. So these are few of the control signals which are given by the 8086 microprocessor. First we will study about ALE. Its full form is address latch enable. So this signal is used to enable the address latch. When this signal it is at logic 1, then this latch will be enabled, and on the multiplexed address and data bus, when this logic is 1, then address will be available. So this ALE signal, it is basically enabling the address latch. So when this latch is enabled, then address is going to be available on the AD0 to AD15 address data bus. Okay. Next we have the bus high enable BHE. This signal, it is also used as the S7 signal. So when this signal it is at logic 0, it is used to enable the memory operation. It is the memory enable signal. Okay, and when it is logic 1, it can be also used as the S7 status signal. Next signal we have are the memory input output signal. This signal is used to decide that whether it's a memory operation or an input output operation. So when this signal, it can have at logic 0 also and logic 1 also. So when it is at logic 0, it's an input output operation. And when it is at logic 1, it is a memory operation. Okay. So this is going to decide that whether the read or the write operations which are performed by 8086, they are related with memory or with the input output device. Then we have data transmit and receive. This signal is used to decide that whether the data it is going to be transmit or received by the microprocessor. So when this is at logic 1, data is transmit, and when it is at logic 0, data is received. Okay, so here we have, because memory or input output operation, with this we have read operation also and write operation also. So for read we have the control signal RD bar, and for write we have the control signal write bar. So when the signal is going to be read by the microprocessor, then data is received. So this data receives signal that is going to be at logic 0 for the memory or the input output read operation. When the data is to be written on an output device, so at that time data is going to be transmit by the bus. So this DTR, this line, this will be at logic 1 for the memory or input output write operation. So these are few of the control signals. One of the control signal is also the ready signal. Now, whenever the microprocessor, because it is interfacing with the peripheral devices, so suppose that the speed of processing of some peripheral device, it is very slow, and the microprocessor, it want to communicate with such slow interfacing device. So that device will be having this signal ready signal. That ready signal will be sent by the peripheral device to indicate the microprocessor that it is ready for the communication, for the data transfer. So it is sent by peripheral devices to insert the wait state in the microprocessor. So when wait states will be inserted in the bus cycles, then microprocessor, it is going to take some time to execute the instructions or to complete its working. Okay, so that time will be at that time, in that period, that is the wait state period, the peripheral, it is going to cope up with the speed of the 8086. So ready signal, it is sent by the peripheral devices so that wait states can be inserted in the microprocessor, so that it can take some long time to complete its work, and at that time the peripheral will become ready for the communication. So these are the control signals which are used in the minimum mode interface. Next we have the interrupt signals. In the category of interrupt signals, we have INTR, which is the interrupt request signal. Then we have INTA, that is interrupt acknowledge signal. In 8086, we have a NMI, that is non-maskable interrupt also. Also, we have the reset signal and test signal. So these are the some of the interrupt signals. This INTR, it is the interrupt request which is given by some peripheral devices to the microprocessor who wants to interrupt the microprocessor. So whenever this INTR pin, it is active, means it is at logic 1, it means that microprocessor has been interrupted by some peripheral device, and that peripheral device, that microprocessor should jump to a memory location where the interrupt service routine is written, and it is going to execute that service routine, return back to the main program, and then execute its further instructions. So this INTR, it is used to interrupt the microprocessor. Now, when this request is given to the microprocessor, in response to this request, this INTA signal will be generated by microprocessor. So it's an acknowledgement signal. So this signal will be given by the microprocessor to the peripheral device that I have received your interrupt request, and I am going to jump at that memory location where ISR is written. Okay. Then we have NMI. NMI is the non-maskable interrupt. This is also a kind of interrupt of 8086. When this interrupt is given, then microprocessor is going to execute the ISR, that is interrupt service routine, and because it is non-maskable, so this cannot be avoided by the 8086. It has to first execute this or first acknowledge this interrupt. Then we have the reset. Signal, it is used to clear out or bring the 8086 to its initial conditions. So when this reset signal will be given, the interrupt flip-flop, interrupt enable flip-flop, that will be reset, that will be made 0. So all the interrupts which are given to the microprocessor, they will be discarded. Okay. Then we have this test also. This is also related with the external interrupt interface. Okay. Now in the microprocessor we have a instruction, wait instruction. So when this instruction is written in the main program, then this test signal will be checked by the microprocessor that whether it is 1 or not, 1 or 0. So if the signal is found to be 1, then the microprocessor, it is going to enter into the idle state. Okay. And when this signal is 0, then microprocessor, it is going to execute the next instruction. Idle state means that microprocessor is not going to perform any fetching or executing of the instructions. It is going to rest. It is not going to perform any of the operations. And when this signal becomes 0, then only the microprocessor will resume the execution of the next instructions. So these are some of the interrupt signals available in the 8086 microprocessor, which are used during the minimum mode interface. Next, we have the DMA signals. The DMA interface signals, we have to hold and HLDA. DMA interface means that direct memory access controller is there. This controller is going to get the control of the buses of the 8086 microprocessor. So when the DMA, it wants the control, it is going to send the hold signal to the microprocessor, and when the microprocessor relieves the control, give the control to the DMA, then it is going to give the HLDA hold acknowledge signals. So these two signals are used to get the control of the buses by the controller, and also HLDA is used to acknowledge, to give the control to the DMA controller. Okay. So this is sent by DMA to request microprocessor to release the control of buses. And HLDA sent by microprocessor to DMA to inform that it has released the control. So these are the DMA interface signals. So in this in this topic, under this topic, that minimum mode interface, we studied the signals which are used during the minimum mode configuration, where all the signals are used by the 8086 microprocessor, and all control signals, they are derived by the 8086. So here in this video we studied about the minimum mode 8086 system. It was the 8086 microprocessor. Clock generator was there, which is providing the clock pulses to the 8086. We have the demultiplexer through which the various memory and the input output read and write signals were generated. Then we have the latches, which are used to separate the address and the data bus, which are multiplexed. Transceivers, which are used to transmit or receive the data. This was the memory section and it was the input output section. We have the chip select signal, whether we want to communicate with the memory or whether 8086 it wants to communicate with the input output device. So this was the minimum mode configuration where only one processor is there, and this processor is providing all the control signals. Okay. So I hope that this topic is now clear to you. Thank you.